In this class, we are going to discuss about examples for sequential logic circuit. There are two types of sequential logic circuits. Those are asynchronous and synchronous. Here, examples of sequential logic circuits. Those are latch, flip-flop, counters, frequency divider, and register. Latch. Latch is a specific kind of sequential logical circuit which have two stable states. They are low and high. So now we are going to see some examples for latch. Here, SR latch, JK latch, gated SR latch, D latch, gated D latch, and T latch. Now, SR latch. Generally, latch is asynchronous sequential circuit in which they are not having a specific clock pulse. We can say these are unclocked flip-flops, and this can store one bit at a time. In a clock pulse, we can store one bit. We can say these latches or flip-flops are one-bit storage devices. See here, this reflects the logic circuit for SR latch. And here I use NAND gate for create SR latch. Here I use NOR gate. Actually, we can draw SR latch using NOR or NAND gate also. Generally, NAND gates are preferred. NAND gate is also same as NOR gate. Structure is same, but only different is set input we are giving into normal port and reset input we are giving in complement port in NAND gate SR latch. And here reset input we are giving to normal port and set input we are giving to complement port. Now, our aim is to get required functionality to the latch. That means to latch need to get no change condition, set, reset, and indeterminate state. Now, I'm going to define a truth table. Before that, I'm going to draw the SR latch here. In the truth table, so what are the input variables and what are the output variables? Which mean definitely for any sequential circuit, the input variables are input and present state. That means our input are S and R, present state is Qn. So totally for a sequential circuit, we are having three combinations of input. That means input and present state. So I'll write S, R, and Q, N. And here, having a complement. This is not a present state. Everyone are going to confuse. This is our present state. And this is our next state. No, this is not next state. This is just the complement of the present state. After crossing these two, that means normal present state and complement, whatever you are getting on this same port, that is called as next state and its complement. So now I'm going to consider my truth table for this SR latch. Here three inputs may be S, R, and Qn, and Q1 plus 1 is maybe my output. So here we don't know what state that is here already. We don't know the present state of latch. We just know what inputs we need to give. That means we are giving some combination for S and R. Present state is already outputted value. We can't change whatever effect is there by the present state that circuit is going to take. So here we don't know the present state. So I'm going to consider the input values for S and R. Those are 0, 0, 0, 1, 1, 0, and 1, 1. Now I'm taking this first condition when we give 0 for both S and R. What may be the next state after crossing this Qn to inside? By either you need to see for a value in normal port. Otherwise, you can write whatever you are getting. Now, I'm going to check the all 4 conditions. So, the first condition is S is equal to 0 and R is equal to 0. For here, we get Qn plus 1. And here, we get Qn plus 1 bar. So now S is equal to 0 and R is also equal to 0. Then here you can see 0 into this Qn bar goes to the input. So we write 0 into Qn bar, and this is the NAND gate, so a whole bar. So 0 into anything is equal to 0, then 0 bar, so is equal to 1. Then here we can check 0 into this Qn whole bar. It is also 0 into Qn is equal to 0 and 0 bar is equal to 1. Here you can observe next state and its complement have same value. Can we get like this? No, we can't get like this. It's practical wise impossible. So it's an indeterminate state. Now I'm going to check the next combination, and that is S is equal to 0 and R is equal to 1. So here 0 into Qn bar whole bar, and it's equal to 0 bar, we get 1 here, and here 1 into Qn whole bar. So here I get Qn bar. So now I can write the value for the next state as 1. Now the next condition. That is S is equal to 1, R is equal to 0. Here 1 into Qn bar whole bar, and it's equal to Qn. And here 0 into Qn whole bar. 0 into anything is equal to 0. And here bar, so 0 bar is equal to 1. So now I can get the value for Qn. I can say, because here the complement value is 1. So normal portion is 0. So now I write 0 here. So this is reset condition. This is called set condition. Then I'm going to move to the fourth condition. And that is S is equal to 1 and R is equal to 1. Here 1 into Qn bar whole bar, it's equal to Qn. And here 1 into Qn whole bar is equal to Qn whole bar. So now I can write Qn here. Here, whatever Qn plus is there, we are getting same Qn. And here, whatever Qn plus 1 bar is there, you are getting same Qn bar. So whatever present state are there, the same present states are continued to be the next state. So this is the truth table for SR latch. Now I'll move to the flip-flop presentation slide. Flip-flop. Flip-flop is a bistable multi-vibrator. The circuit can be made to change state by signal applied to one or more control inputs and will have one or two outputs. Flip-flops are single-bit storage device. We are going to design so many memories by using SR flip-flops. Here, some examples for flip-flop. SR flip-flop, JK flip-flop, T flip-flop, and D flip-flop. Here you can see the circuit diagram for SR flip-flop using NAND gate. Here, I'll again say flip-flops are single-bit storage device. We are going to design so many memories. SR flip-flop is a initial flip-flop that is also called as set and reset. Here you can see the circuit design of the flip-flop. We are going to determine the functionality. See here, this is SR flip-flop by using NAND gate. And here you can observe a clock pulse. Previously, for latches, we are having this section as latch. Now we are giving some clock input to this latch, and it will be changed as flip-flop. Now I'm going to represent my functionality by using truth table. Q and Qn are output, but it's not required output, just present state. Present state is feedback input. Output came from past input. So always you need to check for next state. Next state by taking the reference of this present state and my present input. Whatever we are getting as input, that is for next state. So now here S and R are input and here we have a clock pulse. And it's always high. So the value is 1. Then I'll make the truth table. Those are the 3 inputs of my SR flip-flop. And Qn plus 1 may be the output. Then here also, we don't know about the present state. Then these are the combination for values. Now, I'm going to check the 4 conditions one by one. Here, first, we have 0 to both S and R. So, here, 0 into 1 is equal to 0 and it's a NAND gate. So, we get 1 here. Here also. Now, 1 into Qn bar whole bar for Qn plus 1. One into Qn bar whole bar and it's equal to Qn. For the complement, one into Qn whole bar is equal to Qn bar. So we have Qn for the first condition and it's called as no change condition. Then I'll move to the second condition for this SR flip-flop. Second condition is S is equal to 0 and R is equal to 1. Here we get 1 into Qn bar whole bar and it's equal to Qn. Here we have 1 here, not here. Then 1 into 1 is equal to 0 because it's a NAND gate. So I put 0 here. Here 0 into Qn whole bar. 0 and anything is equal to 0. So 0 bar is equal to 1. Using this as reference, I can say a value for the Qn and it's equal to 0. So it's a reset condition. Then I'll move to the third condition for our flip-flop. One, 0 condition. Here we get 0 and here we get 1. 0 into Qn bar whole bar. 0 and anything is equal to 0 and 0 bar is equal to 1. Then 1 into Qn whole bar is equal to Qn bar. So I get 1 for Qn plus 1 is set. Now I'm going to check the last condition 1. So 1, here also 0. So 0 into Qn bar whole bar, and it's equal to 1. Then here 0 into Qn whole bar. Here also we get 1. So this is also indeterminate state. As we before see in the latch also. So these are the outputs for these inputs. And here's the diagram for the SR flip-flop. Now I'm going to see about JK flip-flop. JK flip-flop is the solution for SR flip-flop because in SR flip-flop there was an undefined state, and that is waste. To use that undefined state, we are having another circuit. We are toggling the input, whatever indeterminate state is SR flip-flop. We are changing that state into toggle. Now we can see. Now we will see the truth table for the JK flip-flop and how we will get the toggle state also. I'll draw the circuit for the JK flip-flop and I'll put the truth table also as we see before in SR legend flip-flop also. Those are same. So now we want to check the condition for this JK flip-flop. First condition, J is equal to 0, K is equal to 0, and for Q n plus 1 and Q n plus 1 bar. Now here 0 and here also 0. So here clock is 1 and so 0 into anything is equal to 1 because it's AND gate. So I put 1 here. Then here 1 into Qn bar whole bar. So I'll write 1 into Qn bar whole bar and it's equal to Qn here. Then 1 into Qn whole bar. 1 into Qn whole bar is equal to Qn bar. So here no change state. So I'll write Qn here. Then move to the second condition or second state. Second state is K is equal to 1. So now you can see here 1 and 1 into Qn bar whole bar is equal to Qn here. And here you can see 1 into 1. So 1 into 1 and Qn. So I'll have Qn bar here. So now Qn bar into Qn whole bar. Qn bar into Qn whole bar. And it's equal to 0, because when we are considering Qn as 1 and is equal to 0, we can get 0 here, and here we have the bar for whole, so 0 bar, and it's equal to 1, so we get 0 for Qn, and it's a reset condition. Then I'll move to the third state. Third state is 1 and 0. For j is equal to 1 and k is equal to 0. Here we get Qn because you can see this Qn bar goes to this input. So 1 into Qn bar whole bar. So it is equal to Qn. Now Qn into Qn bar. And whole bar. Here we get 0 bar, so 1 for Qn plus 1. So I'll write it as here, and it's set condition. Now I'll check this also. So here we get 1 here, and 1 into Qn whole bar is equal to Qn bar. So it's also fulfilled. Then I'll move to the fourth condition, the toggle. Here I get Qn for 1 input. So you can say what input, what output I get for k is equal to 1. I'll get Qn bar here, because 1 into 1 and this Qn comes to this NAND gate, and it's an AND gate, so Qn bar. Now I'll check one by one. Here Qn into Qn bar whole bar, and it's equal to 1, and here Qn bar into Qn whole bar, both are same, and I get 1 here. So it's also, we can't get like this, and now we want to toggle it. Now I showed you how can I toggle it. You can check here 1 into and this Qn bar, you will get Qn here, and here 1 into this Qn, you will get Qn bar here. Now I am just deriving the output of this, and after that I'm processing that input to next state. Now I need to check these two gates. So first I'll check this gate, and this is Qn plus 1 bar. So here Qn bar into Qn whole bar. So here 0 bar is equal to 1. I'll get 1 for this complement. If you want any Qn plus 1, I want to check this circuit. Then Qn into 1. Here I get 1 whole bar and is equal to Qn bar. Whatever Qn is there, that complement I get. So here I get Qn bar. So here Qn and is here Qn bar. So it's a toggle condition. Now I'll move to the presentation slide. And here you can see the circuit diagram of the JK flip-flop. And now I'm going to tell how to draw the JK flip-flop in Logisim. Here I already draw a JK flip-flop, but you can see here I have error. Now I showed you how to delete this error. So first I disconnect those both 4 wires, and now I change the J into 1 and I'll on the clock pulse. Then you can see here I get 1. Then I'll off the clock and after that I connect it. Now you can see JK flip-flop is working. This is the way to connect the JK flip-flop properly. Then I'll move to next section. Counters. The counter is one of the expensive applications of the flip-flop. There are 2 types of counter available: asynchronous counter and synchronous counters. We are going to see about BCD or decade counter. And here you can see the counter circuit. Now I'll show you how is the counter is run. First I click the clock and I select 1 here. Then I'll change the clock again. Here you got 1 here. Then 1 0. And 1 0 is equal to in decimal 2. Then I'll change it. We get 3. Then 4. Then 5. And 6. 7. 8. I'll get 9 here. After the 9, I will get 10. So after the 10, I want to reset the circuit. So that's why I connect the NAND gate for this first and Q1 and Q3, because I want to reset the number as 0. So that's why I connect NAND gate here, because NAND gate change both when we have both input as 1, NAND gate change it as 0. So it's a reset condition. This is a simple explanation to the counter. Now, frequency divider. A frequency divider can be constructed from JK flip-flop by taking the output of one cell to the clock input of the next. You can see this is the output of the one cell and here's the clock input. So now I showed you the circuit diagram of the frequency divider in Logisim and I showed you how it works. Here you can see the frequency divider Logisim circuit. And here I'll make LED as the output for every JK flip-flop output. Then I showed you, I enabled the clock pulse. You can see the time difference that LED on and off state. So here the frequency is divided by the JK flip-flop. And here you can see I'll increase the speed of the pulse and you can see it easily. So this is the small explanation about the frequency divider. And we will see about those examples for combinational circuit in next video. Until that, goodbye and stay safe. Thank you.